Now we explain the design of the multiplexers. As usual, we start by defining what is a multiplexer. Multiplexer is a circuit that selects binary information from one of many input lines and direct it to a single output line. Multiplexer is really, we call it sometimes combining, because if we have one line, if we have one channel here, and if we have 4 users that want to use the line, what we do, we reserve, as an example, 1 second for each user. So we take user number 1 will send his information here, and then 2, and then 3, and then 4. This is 1, 2, 3, 4, and then user 1 again, and so on. And the question becomes how to select one out of these 4 and put it in the line. This is the function of the multiplexer. Therefore, simply, we can say that the multiplexer has 2 to the n input lines in general, and 1 output line, and then we need n selection lines. The selection lines will decide which user we will take its data to put in the line. Let's give an example. The simplest example is 2 to 1 line multiplexer, which means it has 2 inputs that we can call I0 and I1, and of course 1 output as we have just described. And for 2 inputs we need 1 selection line only. We can call it S. So if S is 0, as an example, this will be 0 here, and this will be 1, and this will be 1. 0 and I1, this will be 0. 1 and I0, this will be I0, and I0 or 0 will be I0. Therefore, Y is equal to I0, which means if S is 0, I0 is selected and it appears at the output, and vice versa, which means if S is 1, this will be 1, and this will be 0 here, and this will be 0 here, and this will be 1. 1 and I1, this will be I1. 0 and I0 will be 0, and Y will be equal to I1. So great. Therefore, if S is 0, I0 will be selected. If S is 1, I1 will be selected. This is really the function of the multiplexer. We draw it as a block diagram, a black box, which has 2 inputs, I0 and I1, and 1 selection line. And it's very important to name also the inputs, where do they go. So input I0 goes to input 0 at the multiplexer. I1 goes to input 1 at the multiplexer, and this is the output Y. Why did we write this down? To indicate that if S is 0, this will be passed to the output, and if S is 1, this will be passed to the output. So this is simply the block diagram of the multiplexer. Usually we draw, this is a larger line as compared to this one, to indicate there are many inputs here and 1 input here. That's one way to write down the multiplexer. We move now to 4 to 1 multiplexer, 4 line to 1 line, and this multiplexer has 4 inputs. We call them I0, I1, I2, and I3, and 4 inputs. For 4 inputs, we need 2 selection lines. We call them S1 and S0, where S1 is the most significant usually, and S0 is the least significant. So we write them in this way. And on the left-hand side, on the right-hand side, we see the function table of the multiplexer, which is when S1 is not S0, 0, I0 will be selected. When the selection variables are 0, 1, I1 is selected, and 1, 0, I2 is selected, and 1, 1, I3 is selected. We can confirm this actually by taking any case. Let us take 1, 0, 1 for the selection variables as an example. So let's make S1 is 0 here, and S0 is 1. And if this is 0, this will be here 0, and this will be 0, and this will be 1. So this will be 1, and this will be 1. And if S0 is 1, this will be 1 here, and this will be 1 here, and this will be 0. So this will be 0, and this will be 0. If we look at the AND gates now, the only AND gate that has two input ones is this one here. Therefore, the output will be I1. And all other input gates will have one input 0 or two input 0, which means the output must be 0. So this is 0, and this is 0, and this is 0, and Y will be equal to I1. So I1 is selected. Same thing exactly actually. If we try the other three combinations for S1 and S0, we will find we can verify this function table that it is indeed correct. So if these are 0, 0, I naught will appear here. And if these are 1, 1, as an example, I3 will appear here. So that is the function table of the multiplexer, and how this is how it operates. We can draw it also as a block diagram, as we see here, where the inputs I0, I1, I2, I3 are at the left-hand side, and they go respectively to inputs 0, 1, 2, and 3 of the multiplexer. The selection lines here, we call them S1, S0, where S1 is the most significant and S0 is the least significant, and this is the output Y. So if these are 0, 0, input 0 will appear at the output. If these are 0, 1, input 1 will appear at the output. And if these are 1, 0, input 2 appears at the output. And if these are 1, 1, input 3 will appear at the output. We can also draw it as a triangle, and this is the longer line of the triangle, I0, I1, I2, I3, and this is just one point for the output Y, to say that we have many inputs and we have only one output, and the selection lines always go from the bottom. If we notice, the multiplexer can be drawn as follows, as an alternative to what we have seen. We can, if we pass S1, S0 to a decoder that we explained earlier. Of course, the decoder, if these are 0, 0, this will be 1, and all others will be 0. And if that is 1, this will be here 1, and this will be 0, this will be 0, this will be 0, which means this will be I0, this will be 0, 0, 0, and Y is equal to I0. If S1 is 0, is 1, 0 as an example here, output 2 will be enabled, so output 2 will be 1 here, and all others will be zeros. Therefore, this will be 1 here, and all others will be zeros, and this will be I2, and others will be zeros, and Y will be equal to I2. Therefore, the decoder here actually, it does the function, it produces all the minterms. So the minterm 0 will be active here if the inputs are 0, 0, and I0 will appear here, and minterm 1 will be active here too, so that I1 appears at the output of the AND gate, and minterm 2 will be active here if this is 1, 0, and minterm 3 will be active here if we have the inputs 1, 1, so that I3 will be selected. Now we can go on to show how do we implement larger multiplexers. Larger multiplexers can be constructed from smaller multiplexers, as we have done with the decoders in the past. Let's take an example where we have an 8-to-1 multiplexer that can be constructed from smaller multiplexers, as we can see here. 8-to-1, so we have 8 inputs. We input 4 inputs to the first multiplexer, and this other 4 inputs to the second multiplexer, and S0, S1 are input to both multiplexers, and S2 will be input to another multiplexer, which is 2-to-1. Let's take an example. Let us take the inputs S2, S1, S0 to be 0, 1, 0 as an example here. So if these are 0, 1, 0, it means S1, S0 is 2. So this is 1, 0, and this is 1, 0. So this will be I2 here, which is this one, and I6 will appear here also because it is at this input 2, and this goes to input 0, and this goes to input 1, and this is 0. So Y will be equal to I2, of course, because this is 0. And if we take, on the other hand, this combination 1, 1, 0 for the selection lines, so we kept these to be 1, 0, same as before, so that the outputs of the first two multiplexers will be the same, I2 and I6, but this would be here 1. So 1, this input will be output, and therefore Y will be equal to I6. This is how a larger multiplexer is implemented from smaller multiplexers. A multiplexer can also have, we can also select more than one input. As an example, if we have two 4-bit numbers and we want to choose one of the two numbers, we use this actually of an arithmetic. So we have one number as A3, A2, A1, A0. The other one will be B3, B2, B1, B0. And we want to select all of B or all of A. What do? We use a quadruple 2-to-1 line multiplexer, which means we have as if we have 4 multiplexers, but each of them is 2-to-1. And the 4 multiplexers, they all work at the same time. So they will all select the A's or all select the B's. And if we have an enable input to the multiplexer also, we add it here to make the circuit function or not function. We can analyze the diagram so that when E is 0 here, this will be 1, and this will be 1 here, 1, 1, 1, 1, 1, 1, 1, and the output will depend upon the other inputs. So if the selection is 0, this will be 1, and this will be 0, this 0, 0, 0, and this will be 1, 1, 1, 1. It means A note will be here, A1 will be here, A2 will be here, and A3 will be here, and all these will be zeros. Therefore, Y will be equal to A. And this is the case that we have done here actually. So we select A in this case when S is 0. On the other hand, when selection is 1, if this is 1, this will be 0, and these will be zeros here, and these will be zeros, and the 1 will be here. So this is 1, 1, 1, 1, and the B note will be here, B1 here, B2 here, and B3 here, and Y will be equal to B. On the other hand, finally, if the E is 1, notice if E is 1 here, this will be 0, and 0 will be given to the inputs of all AND gates, and therefore all outputs will be zeros, and we say that nothing is selected. So this is how we can construct a multiplexer to choose one of